Hello everyone.
Hi.
Welcome to this webinar here today. Let me just readjust the presentation here. All right. Yeah, it's a pleasure for us to be with you today. Thanks for joining. So this today, yeah, we'll be talking to you about our most recent hyperspectral instrument, the HyperCam Airborne Nano. So my name is Jean-Philippe Gagnon. I'm a field application engineer with Telops, and I'm joined also today on this webinar by my colleague Marc-André.
Hello, I'm the product architect for the hyperspectral imagers.
Yep. But first, before we dive in, let me just remind you that this webinar is being recorded, and a link to the recording will be sent to all attendees in a follow-up email just after this webinar. Also, we also encourage questions from the audience. So if you hear something that sparks an interest, or you would like to get more information on some of the topics that will be discussed here today, feel free to just open up your GoToWebinar question box and type it right in. We'll reserve a few minutes at the end of the webinar for a short Q&A session with you guys. So yeah, feel free to throughout the webinar throw in your questions and comments, and we'll have a look at them afterwards.
If we don't have time to answer the question, you can send them, and afterwards we'll contact you to maybe have a quick chat with you.
Exact. Yeah, that's a good point. In fact, all the questions will be logged, and if for some reason we can't go through all of them at the end of the Q&A session, we'll make sure to answer them in a follow-up email to all of you who has registered. All right, so let's dive right in our main subject today, which is HyperCam Nano. So why does it matter? Why are we building this this new equipment? Well, it stems from the fact that from the last few years we've seen a shift. So researchers and operators out there want the power of high-end hyperspectral capabilities, but with the agility and flexibility of small UAV platforms. So they want added agility from their hyperspectral systems, of course, react faster, deploy in remote areas, and collect high-resolution data that satellites or manned aircraft simply cannot capture, all while, of course, keeping costs down. An important aspect. So, for instance, the oil and gas and chemical plant operators out there, both on land and offshore, need to inspect their facilities for methane, for example, or other hydrocarbons or VOCs, volatile organic compounds. Fugitive emissions, also perform rapid gas detection after extreme events, for example. And in addition, geologists want centimetric scale mineral mapping on rugged terrain, while the defense and security teams out there need to discrete, precise spectral intelligence. So until now, this level of spectral performance wasn't available on drone platforms without major trade-offs. But that's exactly what changes today with the release of the HyperCam Airborne Nano system. So the Nano has been designed. Oh, you see it here in the video.
It's a real one.
Exactly, it's a real functioning unit that we've got on display here today. So just a quick high-level description of the system. Well, as you may have guessed already, it's a hyperspectral imager fully integrated on a gimbal positioner system. So it's sensitive in the thermal long-wave infrared, so from 7.5 to 12.4 microns. It uses inside a cooled detector, infrared detector, and this provides very high sensitivity, of course. It's got 320 by 160 pixels infrared detector technology, and with my colleague Marc-André, in a few slides, we'll explain to you why it's only 320 by 160 and not our regular 320 by 256, if some of you out there know about the other products that we have. The field of view has been adjusted to fit most applications, so it's 35 by 18 degrees of field of view. And just like all of the other members of the HyperCam family, it's got a user selectable spectral resolution. It can go down to 4 wave number. Again, 4 wave number, not as high or not as fine as the other member of the family, and we'll explain that to you just in a short while. So as you see, the Nano has been designed with drone capability and versatility in mind. So the customer has the freedom to select the drone of their choice here with this product. We, Telops, can also suggest drone options, if you'd like, or we can include it directly in the offer or support you in the integration of the HyperCam Nano with the drone of your choice. So again, throughout the presentation, if you think of a different application where this instrument could be put to use, or you have any comments, or you think we should integrate some other functionalities or instrument, couple this instrument with other type of equipment out there, let us know. Put it in a chat, and we'll read it through at the end of during the Q&A session. All right, so let's have a look before going in too deep here behind the innovation. So the type of challenges and technological breakthrough that the team here at Telops was able to achieve or has gone through while developing this new type of equipment. Before, let me just brush you a high-level historical journey of our historical journey developing hyperspectral systems here at Telops. So this journey began back in 2005 with the development of what we called at the time the first HyperCam, which was the larger 30-kilogram camera, a tripod-based version. And quickly thereafter, the team here went to work trying to make sure that the data that this instrument produced had a real-time, the real-life application. And the first one which was addressed was gas detection back in the days. So in 2006, we did our first instrument, not instrument, but experiments, detecting gaseous emissions from a ship that was sailing on the ocean. And you can see it in the top image. The blue is the gas being detected and emitted by the ship and being detected by the camera. That was in post-processing, no real-time capabilities at this point. After that, we put the camera on an airborne platform for airborne survey measurement. This was quite bulky instrument. I don't know if you remember. Pretty large system.
Heavy.
Exactly, very heavy, very difficult, not very portable, but nevertheless very capable system. After that, in 2010, we spent a lot of time trying to make put the algorithm that we use for gas detection work in real time. And we did that for the tripod-based camera and, of course, with the airborne system. In 2020, the team here had a mandate to start the miniaturization process of the camera itself. And so that was done with first our airborne system. That led to the launch of the HyperCam Airborne Mini in 2021. And then the HyperCam, the ground-based version, the HyperCam XLW in 2022. And now, 2025, we've miniaturized things even further with the HyperCam Nano that you see right here. So, just a few words about the inner workings of the camera, just to illustrate or try to help you understand a little bit more how the data is being produced. So inside of the Nano, just like our other members of the family, sits a Michelson interferometer or a Fourier transform interferometer. So this is a special type of optical equipment that has a beam splitter in the middle. So it's all based on the interference of light waves. So the light waves come into the camera, splits into two paths or two arms, and we vary in one of the arms the distance between the mirrors at the end and the beam splitter. Short animation to show you just that. So the mirror is being moved along the path, generating a path difference, and a interference pattern at the detector level, and that's what we measure. It's the intensity of that interference pattern. So we end up with a series of images, infrared intensity images, that look like that. So we call that a data cube, being acquired at different optical path of the optical path position of the moving mirror. And this generates what we call the interferogram, which is just the intensity level. If you focus on one pixel of this data cube, you get the interferogram. And we take the Fourier transform of that interference signal to get the spectrum out. A little bit more of a detailed picture of what goes on inside. It's basically the same information. This was just to illustrate the fact we took the FFT, we get a spectrum in wave number, and then we have to calibrate the intensity axis. And we do that by performing a radiometric calibration, which is normally do it with just two black bodies,
Yeah.
a hot and cold measurement. Simple as that. And that's what we've been doing ever since with our.
I just wanted to add the path of the mirror, that the movement of the mirror is directly, it affects the spectral resolution. So if the distance that the mirror is moving, if it's smaller, you can't have the 0.5 or 1 wave number. That's why inside the Hypercam Nano, the physics and the science tells us there's a maximum of the spectral resolution that we can achieve in such a small space. That's why the best resolution is 4 wave number inside the Hypercam Nano.
And not 0.5 like
Yeah.
that. The Mini, for example, is able to achieve 0.5, so that means the mirror can scan for a longer distance.
Yeah.
Whereas it's in the Mini, in the Nano, like you said, it's everything's more compact,
Yep.
right? So the mirror has less
Distance.
to move through,
Yep.
and hence this restrict the spectral resolution. Good point.
So
yeah, the net product, before we move on, the net product is of course a data cube made of radiance spectrum. All right, so we've mentioned it earlier, but one big aspect of the development was the miniaturization of the equipment itself. So, of course, the team, I'm sure you know,
worked a lot. Yeah.
had several challenges ahead of them. So, yeah, why don't you spend a little bit of time just
I'm going to
explaining what the team was able to do.
So here you can see the Hypercam, the first Hypercam. You can see the volume and the weight. So it's a really big system, obviously. Then we use that to develop the Hypercam Mini. So you see here the Hypercam Mini Airborne. So it's much smaller. It's easier to work with, to integrate in an aircraft. So then again, smaller, lighter. And now today we have the Hypercam Nano, which is even smaller and lighter. So we had a lot of challenges for the R&D team. I'm just going to do a quick summary of them. So mechanically, everything, like I said, needs to be smaller and lighter. So each component was looked at, and even each screw was chosen carefully to not add too much weight to the system. So if you look, each screw here was chosen carefully. Electronically, the board needed to be smaller. We even stacked some of them. So the power management is way different. It's really different than the Hypercam Mini. And on the software side, you don't really see it inside, but the software side, all the algorithm for tracking and pointing needed improvement to ensure a full coverage for the full support of the new feature and new angle of the Hypercam Nano. So all the software was improved, and optically the entire system needed to be redesigned. So the optical path is different. Like I said, like GB said, there's a Michelson interferometer inside, so you have to choose each component to make sure that it fits properly. So talk about the detector, which, like I said, GB said, it's not a 320 by 260. Now it's
What, 320 by
160. 160. That's because the smaller size, the interferometer, even the interest window was all looked at optically. One big challenges for everyone was the heat dissipation, because you have a such a small system. Obviously, the heat, you have to manage the heat. That's that was a big factor here for the Hypercam Nano. So the R&D team worked really hard on that, and we are proud of it today for sure. And I just want to point that we don't see any CPV here. Even in the presentation, we don't see the CPV. The CPV is the control and processing bar. So all the processing here for the Hypercam Nano is inside. So basically here we have the optical head, but also it's a mini PC inside. So everything is included inside. After all that, we had to mount it on a gimbal and then on a drone. So you can see was a big challenge. I think the R&D team is really proud of it. So, and yeah, we are really excited today to present it to you.
Exactly. And one thing we can say also is that with respect to the thermal management of the whole thing, the Nano is completely sealed up, so there's no dust or anything that can get in. So everything is conduction cooled, right? That's why you see the fans at the front end here are meant to cool down the camera. Talk about the size here. You get you have the dimensions here in centimeters of the optical head. So basically a cube of 175-ish millimeter. The weight is also really a concern, as Marc-André was just telling us. So it's under 6.7 kilograms here, including the gimbal mount. So it fits pretty well with octocopter drones on the market today, heavy lift drone copters. Power consumption also was always in the back of the mind of everybody here in the R&D department, because the drone will needs we get the power from the drone batteries, and so we have to limit the amount of power consumption that the camera
each needs. Prototype that we did, each had their own drone. So I think we had 4. Each one has a different drone. So we are really proud to be able to. It's easily mountable on basically any drone. So yeah, that's a big plus for us.
Yep, very compatibility with drones have been really thought about. As far as talking about the drone, to attach the module to the drone, it's a pretty simple system. It's just a quick release circular mount, as you can see here on the video. So it really installs in a few seconds, really.
It's a one-person operation. So
yeah, one-person job, and it's only 6.7 kilos. And attachments, it's pretty fast. Talking about the power budget, the R&D team did a good job at minimizing the power. And I've talked about, you remember a few slides back, I talked about we had to do a radiometric calibration to go from just the standard spectra to calibrated spectra. Normally, this is done with 2 black body units, or at least one, but 2 measurements, a hot and a cold black body measurement. And with the other members of the family, we attached black bodies at the front of the camera to do just that. But now with the Nano, we couldn't do that for 2 reasons, mainly power consumption and also the weight consideration. So we had to let go of the black bodies. So what that meant was that the team here had to think of another calibration scenario, and a good thing for us. We developed our permanent calibration a few years ago, and our line of fast camera that we offer at Telops benefit from this permanent calibration. So we took that over and implemented it in the Nano. So now the Nano doesn't have any black bodies attached to it. It's permanently calibrated here in factory. So what that means is, you know, when you fly it, you have 100% duty cycle. Basically,
Yep.
you spend your time collecting optimal data and not spending time in the air, you know, wasting battery power just calibrating. So that's a big improvement on the Nano, the way it flies. So no in-flight or ground calibration required. So again, you maximize your time in the air. But also there's a few well, we thought of a few scenarios in which the permanent calibration needed some fine tuning.
Yep.
So in it, we've implemented just a quick shutter basically that's there to fine tune the calibration. So it's there. It's taken into consideration by the software. It's a really fast procedure. So in case you run into this specific scenario, the software will just guide you and
Yep. The software will tell you the calibration is not optimal, so you can put maybe the shutter on. It will take maybe a few seconds, and you're good to go back to acquire data or back whatever you were doing. So it's really used. It really depends on the application, and don't worry, the software will tell you and guide you through it.
that little
Yeah.
like a little tweak that needs to happen. Yeah, so of course we're using the permanent calibration. That brings about another advantage, is that the Nano operates with an automatic exposure control. So every, you remember the first few slides, the instrument just collects several images of the intensity and with the specific exposure time. If that exposure time isn't set properly, you're at risk of, you know, saturating the image or underexposing the image. So it's critical that the exposure time has to be set properly. And with the Nano, everything is done by the Nano itself based on the measurement that it's doing at the moment. So it will readjust its exposure time. So for the user, what that means is that you're collecting optimal data every time. So that's really important for us. Also, noise on the noise related, as usual, we measure it in terms of noise equivalent spectral radiance, or NESR. And the level of NESR for the Nano is similar to the other members of the family. So I think, again,
I think it's the same as the Hypercam Airborne. So
Mini.
Yeah, Mini.
So I think the R&D team did a very good job at, you know, keeping it in check during throughout the development of the project, and make sure at the end we get a system that is able to provide signal to noise ratio relative to the other members of the family. So what that means is that if you're trying to detect gases, basically you get the same performance, same detection level as the other members of the family. Spectral resolution, we touched on that subject a few slides ago. The Nano is a little bit more restricted or limited than the Mini. So the spectral resolution that it can achieve is 4 wave number.
Yep.
So that translates into around 150 spectral bands at 4 wave number.
That's well enough for gas detection, you know, scientific application, geology, and
Exactly.
so don't worry about that.
So even though the Mini, for example, can go down as low as 0.5 wave number, this is not always a good idea to go very low in spectral resolution, because the finer spectral resolution you go, normally your acquisition time increases.
Yep.
So it's always a trade-off or a fine balance to achieve between all of the different parameters. So spectral resolution, time, acquisition time, and others. So with the Mini, with the Nano, 4 wave number is sufficient for gas detection, just because it provides a good trade-off between spectral resolution, fine adjustment of the spectral resolution, but also the acquisition time. So because you have to remember that the Nano here has to stay on target for the duration of the acquisition.
Yep.
So at 4 wave number, for example, you're maybe looking at an acquisition time of around 1 second, a little bit less maybe. But during that 1 second, it's really important that the system stares at the ground or at the scene and keep that steady for that amount of time. Yep. Otherwise, it leads to some artifacts in the data acquisition. So the Nano doesn't have, like the Mini, a fast scanning mirror to compensate for the vibrations and movement of the aircraft. This one, it's all handled by the gimbal itself.
Yeah. So the mirror is basically the gimbal.
Exactly. In this case, the gimbal's job is to maintain the camera on target for the duration of the acquisition. All right. Yeah, let's look at a few operational scenarios. Yeah, the operational modes here for the Nano are basically the same as the Hypercam Airborne Mini. So if some of you are familiar with the Mini, you won't be surprised to see any of these modes.
It's exactly the same thing.
It's exactly the same.
Same software, everything.
So the first operational mode is you may want to survey an extended area and collect multiple data cubes over that area, and then stitch them all up, create a georeference mosaic with all of your data. And that's what we called the mapping mode. So it requires several data cubes with a certain overlap to make sure we cover 100% of your intended area. The other mode is we call it targeting mode, and this is a little bit different in the way that the system basically all it needs is one single GPS coordinate on the ground, and the system as soon as the Nano is able to lock on the target, it will start acquiring automatically the data over that target for as long as it can basically. So if you fly the drone overhead, it will continue to record data off of that single GPS location. And this is a good operational scenario if you want to investigate plume dynamics, for example. You want to see how the plume is moving as a function of time, or you want to collect several images of the ground to average them up and lower your signal, increase your signal to noise ratio, lower the noise. This is a great mode for that. The next one is what we call corridor mapping mode. And this is a mode that was specifically thought of for pipeline inspection. So for pipeline inspection, you have this long pipeline track that one needs to inspect for potential leaks. And so, of course, the aircraft or the drone won't be able to follow that line, especially if it's got some sharp turns in it. So this mode was designed for that. You see it here. In green, that's the pipeline track. In red, those are the segments or the coordinates that the system will track. And on top of that, the blue is the actual path of the drone or the aircraft, and you can see it's smoother, of course, than the pipeline. But the data that will be collected is right on top of those red inspection ground lines. As you can see here, these are all the individual data cubes that were collected, and sure enough, they all fall right on top of the pipeline. And of course, one thing that's really important is that we must ensure 100% coverage, even in those sharp turns, because pipeline operators, for example, they want to inspect 100% of their assets and not just some portion.
So pre-flight, you're able to prepare your mission. So you select your pipeline or your site or whatever, and you can, after that, simulate the path of the aircraft, and you will see if you have 100% of coverage. And after that, you just follow the path. Even some drone, you are able to give them the flight path, and they will do exactly that flight path. It will come back to you with 100% of coverage that you selected.
A new mode, though, specifically for the Nano, was forward-looking or side-looking. So the Nano can be angled up to look at right in front of it or the side look. So that's a mode that is very interesting for, let's say, mine face, or so you have a mine wall that you want to inspect. You can have the drone fly and just map the whole thing, or an offshore platform. The drone is great for looking at it sideways and see if there's any fugitive emissions. Another operational mode is ground-based. So the system is able to operate without any drones. So you can simply install it on the tripod and measure, let's say, your samples, and then pick it up from the tripod, install it on the drone, and go offline.
That picture is about 3 to 4 weeks ago, so
exactly.
It's real data. It's a real picture.
It's as Marc-André said, this is not our first unit, so we've already have a few of them out there, and one of them is installed at the Helmholtz Centrum Institute in Germany, and the professor there, the researcher, Richard Glo again, was sent us this image of him in South Africa for a measurement campaign. Field of view and visible camera. So of course, with the Nano, you have the infrared imagery at all times, but also there's a visible camera attached at the top, just above the infrared entrance window. It's a high resolution visible camera, so you have the specs here with a field of view that's larger than the infrared field of view, so it provides contextual information. It's fine enough. Also, the camera has a spatial resolution high enough to be able to work with data. For example, if you want to do a change detection, basically have the Nano fly, and then a week or 2 weeks or a month after you fly it again, you can compare data and see if, for example, over your pipeline, there was some construction or some trees that may have fallen on the pipeline. So you can do all that with the visible imagery, as well as with the infrared imagery. Field of view, I've put down here a few examples of AGL, height above ground level, if for flying the Nano, corresponding GSD, or ground sampling distance. That's the size of a pixel on the ground. Here, if you're interested in other values, just let us know, and we'll provide, we'll guide you through the different values here. But theoretically, they now can fly from 50 meters up to whatever altitude you want, or the restrictions are. As Marc-André said, there's in a typical flight scenario, the first operation that needs to happen is the mission preparation. So that's the phase where you determine ahead of time the parameters, the areas you want to scan, the operational mode you want to operate in, mapping, targeting, pipeline tracking mode. So you determine that, and we have a specific tool, a specific software, as we call the mission planner software, that will guide you through these steps. And it's
the same software than the Hypercam Mini Airborne. Exactly. So if you have experience with that,
it's exactly, won't be surprised.
Yeah.
It's the same software, just different instrument. And then you basically, once you have the mission preparation done, basically the output is just a simple file, parameter file that you load into the Nano, and then you can go off flying and in flight. That's basically what it looks like. So the Nano, in this case, it's just a gas release experiment that we did several times, well, a few months ago.
And you can see the work of the gimbal. The gimbal will track the target on the ground, so it's really easy to fly. So you don't need to adjust the drone. The gimbal will do all the work.
To maintain to maintain lock on target. And on the right hand side, this is what exactly what the operator of the system would see on the ground. So on the ground, you have Reveal Airborne running, which is our software. So it receives the imagery from the data, along with the statuses of every subsystem, so you can keep an eye on the actual health of the system in flight. And if you have the gas detection package available or enabled on your system, then you'll see exactly what the picture on the right is showing us. So I think that was Freon 152 for those who might be interested in knowing. So Freon 152 was released in a field, and the system detects it in real time and present to you the results here in green.
Yeah.
See here.
A quick note: all the data is stored inside the Hypercam Nano, and you can have access to the data after the flight. So there's no data transmission live. Everything is inside the Hypercam Nano.
Yep. So all that's being transmitted at the base station while you fly is the processed imagery and the statuses of the system.
Yeah.
And after the flight, of course, we've got different post-processing software. One of them is the Reveal Processor. So that's a software that allows you to look at the data you have already collected, either recalibrate if there needs to be, but with the Nano, that's not necessary because it's permanently calibrated. But if you have the gas detection package available, for example, you can rerun it with different thresholds, if you like, or different gases, and see if you have a detection somewhere.
You will see the spec of each pixel. So if you want to play with data, that's exactly what it's meant. I don't know if you see,
I'll run it again.
But for each pixel, you will have the radiance. So that's all in the post-processing software.
It's not showing.
It's not showing, but
normally it's in the black section down below. You have the actual measurement and spectrum.
Yeah.
Yeah, great tool to analyze the data, do a first-hand analysis of the data, especially helpful if you have the gas detection. Yeah. But again, feel free to comment or let us know in the chat if you would be interested in having more features here. What kind of added functionalities would be helpful for you. We're always open receiving suggestions from our.
We are making the software for you guys, not for us.
Exactly. Last one is our geo rectification tool that allows you to, from a list of individual infrared measurements or infrared data cubes, create large area mosaics, geo-reference everything. You see an example here of several data cubes. I think there's a few hundred data cube being mosaic and geo-referenced in this way. So you can geo-reference, of course, the hyperspectral infrared data, the visible imagery, and also the gas detection layer. Again, if you have that enabled, you can geo-reference everything and generate TIFFs that can be overlaid in Google Maps or in Google Earth or any other ArcGIS software that you are using. And a nice example of our system already deployed and operated in operation in Germany and other, again, from our client and the Helmholtz Centrum Institute in Germany. They have a functioning unit, a Nano, and they're using it for mineral mapping, geology. And that's what you see here. The Nano is taking off, ready for its mission. And on the right-hand side, Richard, go again. Thank you again for sending us the first imagery here. This is a mine wall with different mineral identified, and you can see them in color on the mine face here. It's pretty neat to look at. All right, so we're already at the end of our presentation here. So key takeaways here. I wanted to keep it short. So only two things that we want you to remember about the Hypercam Nano is one, it's our most advanced high-end thermal hyperspectral scientific product here at Telops.
Yeah.
So you've got everything embedded in it, and we've talked about the main features, right? That makes your life easier. So you don't have to worry about exposure time. You don't have to worry about much.
You don't have to worry about calibration. You don't
Exactly.
have to worry about the CPV connecting to the optical head. Everything is there.
Everything is
So
embedded and automated, and as much as we could. And also, it's quite an agile way, agile sensor, very versatile to capture very high resolution hyperspectral data in the thermal infrared region.
yeah.
So on that note, again, thank you for your
Yeah.
attention, and we'll have a look at the question.
Sure. Yeah. I don't know, JP. I know we had one question already about can we use the Hypercam Nano without the gimbal?
Yeah.
But like we said, the gimbal replaced the fast steering mirror. So right now the Nano, you have to you need the gimbal to adjust and do all the targeting and mapping modes. So no, it's not possible to use the Nano without the gimbal. Yeah.
All right, so our first question, so is the radiance data immediately available in real time on the ground computer? So I think we've answered that. As unfortunately not, the data all resides in the optical head. So, but as soon as it lands, you can remove the data off, copy it off, and then
the radiance is inside the SSD.
And that's a good point. I mean, I've had this question before, and it's definitely something that we'll consider in the future to see if we can stream the portion of the actual data off mid-flight. That's a good suggestion, and we'll definitely have a look at it. Yeah, can you briefly explain again how the spectral correction is done? Yeah, so spectral correction, spectral calibration is pretty much a given if we use a Fourier transform transform spectrometer like this. As inside of this equipment, we're using a laser diode to quickly or measure very accurately the displacement of the moving mirror. So the displacement is all being registered by the interference pattern of that laser signal. So by doing so, when we do the Fourier transform, the spectral calibration comes out naturally from this step because we're measuring it with our laser system. So that's how the spectral calibration is done. But after that, there's no spectral correction needed. Yeah, acquisition rate. Yeah, thank you, Ethan, for your question. Acquisition rate, yeah, really depends on a few parameters. So I think I know we said roughly 1 second or shorter. I have tables here. Maybe I can, because you ask, maybe I can in the question and answer document that we'll prepare for all of you guys. Maybe I will insert data acquisition chart as a function of
multiple factors,
multiple parameters. So spectral resolution, acquisition time, size of the infrared window again, because we've mentioned it's 320 by 160, but that's the maximum size. So of course you can reduce it down, and that has the advantage of increasing the data rate, similar to the other member of the Hypercam family. So if you don't mind, I will answer that in the written document. Yeah, optics. Maybe we didn't talk about that. Well, we did mention that the optics is the field of view is 35 by 18 degrees, and right now it's the only optics available. For the Mini, I know we designed different optics in the past. For the Nano, it's not currently in the works, but yeah, if
you're interested, let us know, and maybe we'll look into that.
Well, exactly. If the field of view that we've selected doesn't really match your application, let me know. And yeah, this is this is interesting for me, and I'll be able to put it in a roadmap if it makes sense, and offer different optics. But from a technical standpoint, nothing prevents us from designing custom-made field of views and custom-made optics. But for now, the one that we have is the only one. Yeah, just okay, just running through the drift. How does it overcome the drift and aging? Oh yeah, that's maybe an interesting one. So how does it overcome that? We're talking about the permanent calibration. I think that's what this gentleman here is referring to. So how does it overcome the drift and aging using the permanent calibration? So and this is really an interesting question, and we've measured it with our line of fast infrared cameras. As I said, this permanent calibration is already was developed several years ago and is in operation in our line of fast cameras since, I want to say, 10 years maybe. So we've been able to monitor the performance of the permanent calibration over the years. You know, receiving an old camera that we manufactured 8 years ago, we got it back in service and we checked the permanent calibration, and it's still right on point. Yep. So it doesn't drift, it doesn't change unless, you know, unless your window is dirty or that the infrared detector is broken, then the permanent calibration doesn't hold. But if the camera is in condition, then the permanent calibration stays
up to date.
And we have no reason to believe that this would be different from the Nano. Yeah. So it's using the same infrared detector technology, optics. So if everything remains the same, the calibration will hold true. And one thing we can say also is the user can check it at any time. If you have a calibration module, you can just put it in front, record a measurement, and check that the calibration is still good.
And if you have any concern or question, you can always contact Telops, and we will work with you, no problem.
Yeah, how important is the gimbal? Well, really important. Yeah, it's unlike the Mini. So the Hypercam Mini uses a fast steering mirror installed, you know, inside of the optical head itself. So the steering mirror is the one that keeps the image steady on the ground during data collection. For the Nano, we couldn't do that, again, because of weight, dimension, and stuff like that. So we couldn't go the same way. So that's the gimbal's job now, to take the camera and keep it steady for the duration of the acquisition. So that's why it's an integral part of the Hypercam Nano. Yeah, I see a lot of questions about the data rate, so I'll definitely include that. Yeah, okay. I mean, increasing signal to noise. GP mentioned something like increasing signal to noise by averaging data cubes. Yeah, while discussing the targeting operation, again, elaborate on that. Is that the same as reducing NESR by averaging? Well, it's just regular data averaging. So if the Nano is able to collect the same imagery on the ground, keep it steady, and record multiple data cubes, you can average all of those data cube up. So the individual, well, the NESR doesn't change. It's just that you're increasing your signal. So increasing signal to noise, basically. By doing so, just following the same averaging logic. So if you're taking 10 acquisitions and averaging them up, you'll increase your signal to noise ratio by the square root of 10. So it's a standard averaging scenario. But for that, you have to make sure that the Nano is averaging good data. And not averaging different scenes. Is there an anti-vibration mount needed on the drone? Is it the gimbal is?
Yeah, gimbal is enough.
The gimbal is enough. It's high-end gimbal system, so it's able to reach the stabilization performance.
You don't
that
need
are
any
required.
specific drone or it's all the gimbal.
Yeah, is quantification available for gas detection? And can the software running on the ground station be streamed to external software? Okay, well, quantification is not available. So our gas detection and identification package that we call Reveal DNI is still an option for the drone. But it's doing both detection and identification of the gaseous species. So it's not at this moment, our quantification is still in the research and development phase. So it's not readily available off the shelf, for example. But that might change in the next
future.
in the future. And can the software running on the ground station be streamed to external software? Normally on the ground, you'll be interacting with the Nano through our Reveal Pro 6 software. Same software that is used with the XLW, our normal tripod-based system. So there's an API, of course. There's an API that one can use to interface with the system if you don't want to go through the Pro 6 software. So API is available just like the other systems. So yeah, in this way you can be streamed to an external software. Yeah, I'm not sure if that's exactly what you meant, but yeah, you can interface with the Reveal Pro 6 or through API. I think we'll be able to get as much. So yeah, what typical flight times for the sensor? I think for the ones that we've integrated and tested here was around 30 minutes of flight time with the drones that we've selected. Of course, this will change depending on the drone that you select. Higher capability, higher capacity drones normally have larger batteries and can fly longer.
It's all about the drone. That's
really
the point.
Exact.
So it will be different for different drone.
But yeah, normally 30 minutes. You can. The neat thing about the Nano is that it's got a dual power input logic at the back. So for example, you may have the Nano sitting on the ground, ready. If you want to power it up, you can hook it up to a generator or a regular power supply or ground electricity, and then and then have the batteries connected as well for the drone. As soon as you're ready to take off, you can just pull on the AC power outlet, and the batteries will automatically
take over, and the system doesn't need to be shut down, and everything will run smoothly. So on the ground, you will not use the drone battery. If you plug it in the wall or whatever, you will use that power, and when you're ready to fly, just unplug it, and the drone battery will take over, and it's seamlessly.
Yeah, exactly. Yeah, seamless operation. So it's a great mode if you want to test something before a flight.
Yeah,
you can have your AC connected, so you'll not be draining the batteries of the drone. And as soon as you're ready, pull the cable and then go flying. Manita also asked, you said you have some drone options. Can you recommend some companies? Yes, we have a company, or we have a drone that we've integrated in the past, a US-based drone that we can recommend. But there's so many regulations and so many export limitation, export requirements that it's hard to offer one drone that fits, that can go global. So we have several options. And of course, any single options comes with multiple sub-options, such as radio communication ways, batteries, and stuff like that. So it's best that if you're interested, just contact us, and we'll be in touch. And our team and you will work together to identify the perfect drone for your application and for where you are exactly in the world. All right, I think we've. I don't want to go over an hour. So I think we'll stop here for the time being. Just remember that this webinar is recorded, and a link will be sent to all of the registrants. But give us maybe a day or two to pull it all together. And also the questions have been logged, so we'll go through it after, make sure we've answered everyone. And like I said, a Q&A document will be provided along with the recording, so you'll have all your questions answered for sure.
Well, thank you very much, JP. Thank you, everyone.
Pleasure. Yeah, it'll be very nice to do it with you here. So I hope you guys out there enjoyed it. Just be sure to follow us in our LinkedIn, newsletter, Facebook. We'll do other webinars on the Nano itself next year.
It's the first webinar. It's not the last.
It's definitely not the last. We've got different measurement campaigns planned for 2026. So a lot of new development as well. So yeah, we'll keep in touch.
Yeah.
Before we let you go, I want to wish you all
happy holidays.
Happy holidays. Have a good rest.
Yeah. And see you guys in 2026.
All right. Bye-bye. Enjoy the rest of your day.